Today we're going to be talking about, well, you can pronounce this one of two ways, your pick, MCSema or McSema, and it is a framework that we've spent the last 2 years writing to perform translation of X86 instructions into LLVM.
So we have to have the obligatory introduction. My name is Artem Dinaburg. I'm just a generic security researcher. I've done a lot of research on things like malware analysis frameworks, how cosmic rays can affect your electronics, and now I'm doing stuff with program analysis.
My name is Andrew Ruef. I'm a PhD student at the University of Maryland, and I also work for this company called Trail of Bits. I spend most of my time focusing on programming languages, security, and program analysis. At this point, I would also like to mention that all of the work that we're presenting has been funded by the Defense Advanced Research Projects Agency, also known as DARPA, and that anything that we say or any opinions that we hold or may hold are not the opinions of that agency or indeed the United States government.
You will notice that this disclaimer is on every slide.
Yes. They made us do that.
Yeah. So what is McSema? This is, I guess, the obligatory elevator pitch. McSema is a framework for translating existing binary programs into LLVM. And LLVM is both a compiler and program analysis framework and an intermediate representation. And once you have a program in LLVM, you can use the really rich set of program analysis and transformation tools that LLVM provides to operate on your existing application. And currently, I want to say that right now, the input programs that we take are Windows 32-bit binaries only, but that's not a fundamental limitation. That's just simply the implementation we chose. It is extendable to Linux and other binary programs, and for a while, we actually had a Linux beta version. And now, Andrew's going to talk a little bit more about LLVM.
So, what is LLVM? This is kind of a complicated question to answer because over the life of the project, it's been about 3 distinct things. It's been a language, it's been a compiler middleware, series of libraries and applications, and it's also been a virtual machine. There was a point in time where the acronym expanded to low-level virtual machine, but that point in time has passed, and now we simply refer to it as LLVM. Also, occasionally, we will refer to the language, sometimes as either LLVM IR for intermediate representation, or if I'm pressed for characters, simply LLVM. So LLVM sort of forms this basic substrate of compiler middleware logic that you would want if you were creating a compiler and code emission system for a new programming language or an existing programming language, or if you were analyzing code. And you can analyze any code either that you sort of parse from a source code or that you massage through some other system, like the system that we wrote, into LLVM. And well-formed LLVM should be palatable and parsable by any tool that consumes LLVM, no matter what its source, with a few caveats and restrictions. So what is the intermediate representation and what does it look like? So one reason that LLVM is cool for program analysis, and it's also kind of palatable and useful to people like us, is that the assembly language, the intermediate representation is a kind of assembly language. It's an assembly language for a CPU that doesn't exist, a virtual CPU. The assembly language is strongly and statically typed, and it is static single assignment. So if you look at the slide, the values that are defined %1 equal, %2 equal, those are all in the SSA parlance registers. And in an SSA virtual machine, there are an unlimited number of registers, which is kind of unrealistic. And each register is only defined once and is only written once inside of a control flow graph. This means that this particular property means that you can have these def use chains of values that allow you to sort of traverse from where a value is used to other locations that it is used to the location that it is defined. Having programs in this form can simplify your program analysis and transformation techniques. And algorithms, rich families of algorithms exist to perform conversions to and from SSA and non-SSA languages and perform simplification on code that is in an SSA form. So why would we translate our X86 code into LLVM IR? Well, it will make our analysis easier. However, we can also take existing tools, and there are a large number of existing tools. So for example, inside of the LLVM framework, there are all of the optimizations and analyses that you would find inside of your standard compiler's textbook. So stuff to compute loop headers, identify dominance frontiers, perform simplification, constant folding, dead code elimination. All of these things that if you were to write your own intermediate representation, and many binary analysis projects have, you would wind up with designing a language and designing a translator into that language from your source. And then you would say, great, now I get to open up the Dragon book to page 1 and take 3 compilers classes, essentially, to re-implement everything that's in an existing compiler inside of my framework. So we didn't need to do that, which was great, because we were done by the time we got done translating our code into LLVM. There are also a bunch of existing tools that perform checking on LLVM IR, like CLE that performs symbolic execution, and an LLVM-C tool that performs bounded model checking.
So one of the other advantages of targeting an intermediate representation like LLVM is that LLVM has a very rich set of backend targets. So theoretically, you could take, for example, an X86 binary, you could translate it to LLVM IR, and then let's say emit it as an ARM binary. I mean, obviously, you're not magically going to take a Windows binary and have it run on ARM Linux. Like, you still need to take care of the system call and the operating system interface. But for a lot of the core computation pieces, you can just translate. And if you have some kind of stub layer to translate the system calls, this is a very real possibility. One of the other cool things you can do is that you can take foreign code from an existing binary and integrate it with your own code. One of the canonical examples of this is, let's say you have some malware with a domain generation algorithm. If you can get that malware in IDA, you could just identify the DGA, and then you could take the domain generation algorithm, extract it using McSema, which will only extract the code necessary for domain generation, and then integrate it with your own executable, and then use that to find out what domains this malware is going to generate a year from now. The other cool thing that we can do with transforming existing code to LLVM is that we can take existing binaries and we can add either security or obfuscation to them. Since, for example, Windows XP has been end-of-lifed, you may want to add existing security to your Windows XP components. What you could theoretically do is you could take an existing Windows DLL, you could lift it up to an LLVM intermediate representation, and then you could apply paths such as control flow integrity. Like, there's something on the LLVM mailing list about a guy from Google actually working on adding a control flow integrity pass to the LLVM system. And then you could get essentially control flow integrity for free just by translating your code to LLVM. One of the other options you could do is, instead of just adding security features to your code, you could add obfuscation or anti-reverse engineering features. So there's an actual open source project called LLVM Obfuscator. I think some of the iOS jailbreak code is obfuscated with it. Like, you could take that and then you could use that to apply it to existing binary code. So now it's time for a nice live demo. We decided to do the big live demo early to reward you for waking up and coming here hungover. Let's see this. So, power on. So what are we going to do in this demo? In this demo, we are going to don't quite dare go full screen yet. I'm not sure if that'll break everything. So what we are going to do is we are going to take calc.exe, and then we are going to get all the imports from calc.exe that are present in kernel 32, and we are going to lift the Windows kernel 32 and then re-emit it again and relink calc with it and show that it still runs. So some things to note first. I'm going to run calc.exe, and it's going to tell me it can't execute. So the problem that you're dealing with kernel 32 is Windows system file protection. Like, if you put a kernel 32.dll in your local directory, it's not going to get loaded. It's always going to use the system one. So the difference between this calc.exe and the original one is 2 bytes changing kernel to zernal. I just wanted to get that out there now so you can see that it doesn't run. Now we're actually going to go through with the demo. So first, we set up our environment. Then we are going to run an IDA Python script, which will essentially get all of the imports from the original calc.exe and write them to a text file. And these are only the imports that calc imports from kernel 32. It takes a little bit. You have to wait for IDA to run in the background. There we go. Whoops. Need to move this up a little. Sorry, I'm like operating on the other monitor, so there we go.
He's using his mind powers to read these.
Yeah, so we can see this is a list of imports. So next, so the problem comes when you want to re-emit an existing DLL that references all of the various Windows libraries. In Windows 7, they use a lot of forward imports. So kernel 32 actually forwards a lot of its imports to much smaller DLLs. And so we have some more IDA Python to generate these stub libraries for us. Let me start it. Yeah. There we go. So like this generates all the various stub libraries that we're going to link against. And now we have an IDA Python script that will take kernel32.dll and recover the control flow only for the imports that we previously identified, not touching any of the other code. So it's going to get only the imports and everything that it depends on. And I also wanted to add that like the code that I'm copying and pasting here, this is actually like in the current Git version of McSema. Like this is going to be one of our functionality tests. So like once this is open source, like this will be in the open source directory. Like you can run this example on your own. So now we wait for control flow graph recovery to run. This takes a little bit. It's a big DLL, well, relatively speaking. There we go, finished. Okay, so there's our megabyte of control flow graph. The control flow graph is in a special Google protobuf format that is very easy to parse.
We also ship a schema for it with the source code. The scripts also auto-generate a batch file to take the DLL whose control flow you recovered, and they let you know how to basically give you all the batch file to compile it back out. We're going to make one modification because kernel 32 to DLL is special. We're going to output kernel 32. Now we are going to run our script. Right now it's building the stub DLLs. This is McSema running. You saw it was processing all of the imports. Now it's processing the data that's referenced by those imports, creating special driver entry points, and we'll get to what these are in a bit. But basically, these are needed to take existing context and translate it to the native CPU context. CFG2BC is the main McSema executable. It takes a .cfg file, which is the protobuf control flow graph, and outputs it as LLVM bitcode. There we go, it's done. Now we are running the existing LLVM tools. So opt is an existing tool that comes with LLVM. It's a standard set of compiler optimizations, and we are running this on the bitcode we emitted. One of the things we'll get to further in the slides is that we do a lazy emission of bitcode, and we rely on the optimizer to make it faster for us. This is exactly the same thing that would happen if you compiled a program with Clang from this point forward.
Okay, and so we're done optimizing the bitcode, and now LLC is the LLVM bitcode to object file compiler. And so we are taking the bitcode for lifted kernel 32, and we are compiling it to back to native X86. This is actually the process that takes the longest and gobbles up a lot of memory.
PL tools like using memory.
Yes. All right, it's done. So we are going to run our new calculator, and it runs. And to show that we are not lying to you, we are going to debug attach to it. Attach process. Oh God, so much tiny font.
At the very bottom.
Very bottom?
But which calc is it?
There's only one, right?
I hope so.
All right, so I'm not sure how to change it in WinDebug. Thank you. View. Font, yes. Oh yeah, this is going to get much better.
I learned something. Oh, select the, yeah.
There we go. Oh yeah, thank you so much. Oh, we're not done yet. So this is going to complain a little bit because it attempts to set some breakpoints that can't actually be set. So where is it? 83 to 89.
Yeah.
So let's cause some window redraw events. Come on. Giant fonts.
Ugh.
And you can see it like drawing the buttons, like it's actually using our xernal32.dll, like to prove we're not lying to.
So do a KV5.
Hard to see.
You can tell by the addresses it's us.
There we go.
Yeah. So we have this unwritten application. We didn't modify calc at all except those 2 bytes.
And it's using our, yeah. Now is the clapping time. And like the other like stuff works, like it doesn't just like crash.
It used to.
It used to, yes, but we fixed that. And like you can see, like it's an actual, it actually executes just as it did before.
Add 2 numbers. Yeah.
Yeah. All right, back to the slides.
Just give focus back to it. Then. Okay. Good call.
There we go.
So we're not really the first people to do this X86 to LLVM translation stuff. There has been some prior work in this area. There's a project that was released this year from a group in France called Dagger. They perform a static translation from native code into LLVM, and they have their own model. There are a few differences between everything, what we have done in each of these projects individually that we'll get to sort of as they become relevant. There's a framework from a professor at the University of Maryland called SecondWrite, and that framework performs static translation and recompilation of an entire program. Their aim is to sort of add optimizations and new, I think they have a project where they can add parallelism to a binary program, which is kind of neat. There's a project from Draper Laboratories called Fracture, and they can translate ARM into LLVM, and their code is also available on GitHub. And there's a project from CMU called BAP for the binary analysis platform. They translate native code into their own intermediate language, which they call BIL. But they have a translation layer from their intermediate BIL language into LLVM. So you can translate native code into LLVM by way of BIL. So there are some differences that we will get to.
So since considering all these other projects exist, why did we choose to create McSema? First of all, we wanted something that was open source that people could modify and contribute to. Second, there's documentation and unit tests. Like I know there's documentation because I wrote it. And like we have unit tests, like we use the Google test framework, and we'll get to exactly how those work in a bit. We have FPU and SSC support. And this is something that none of the other projects have. And you run into FPU and SSC code quite a bit. Like pretty much every compiler these days will emit SSC optimized memcopy and memcompares. So like this is something you're going to run into. Additionally, we have a modular architecture where we separate the control flow recovery from the actual translation. And you just saw that in the demo that I gave. Like we have an IDA Python script that comes with the source code that you can take and run an existing DLL, and then the translation piece is separate from that control flow recovery. One of the other tools we originally had was our own custom-built recursive descent disassembler, which caused lots of nightmares, but that's another option if you want to recover control flow. And I just mentioned that this is going to be open source, and Andrew has some more comments about the open source nature of McSema.
Right. So we will open source it. We are interested in open sourcing it. We're doing it. The government needs to tell us we can do it, and then as soon as they do it, it will be done. The government is rather large, I've been told, and these things take time. As soon as it's available, it'll be somewhere on GitHub. When we release it, we're also going to release it under a 2-clause BSD license. I'm told also that this is quite permissive, so anyone can take this code and use it for any purpose, commercial or open source. I think it would be nice if there was more open source binary analysis tools, but if you need to make something private or you want to make some money, I'm also told that money is good. So we can support that too. So we talked a little bit about, we mentioned our unit testing framework. Early in the design of this project, we decided that it would be important for there to be per instruction translation unit tests. Our goal in this project was to make it so that before and after translation, the native instruction and our translated LLVM instructions would be effect identical. So the effects are on memory and on registers. So the way our testing framework works is for every individual instruction inside of our testing framework, we evaluate that instruction in parallel, first inside of a debugger that's based on Intel pin, and second, after translating the instruction through our LLVM translator. And then at the end, we compare the states. So we compare the registers and memory context of the real system, and then we compare the our fake machine context that's produced by McSema at the end. And if the two states are identical, then the test passes. And any differences are failures, aside from differences that are the result of undefined flag behavior, where different physical CPUs will do different things depending on their microarchitecture configurations, which was an awesome thing that we discovered when we started collaborating on this project.
So I mentioned that we have FPU and SSC support, and I want to talk a little more about that. So the slide says that we have nearly complete FPU support. So what does nearly complete actually mean? In that sense, I mean, we support all of the FPU data registers, we support the FPU control flag, and we support a whole bunch of the FPU information flags. We support also many of the instructions, not all of them, but when you're adding instructions, it's simply a matter of writing something that does the actual operations. Like, that's the easy part. The hard part is putting in the register architecture and getting it in with the rest of the translator. That part is done. Now it's a matter of saying, take this register, multiply it with the other one, and put the result in ST0. There are some core issues with the FPU support that are a little difficult to solve. One of the main ones is that the version of LLVM that we originally were writing this on did not have a good way to specify what FPU precision mode your processor should be operating in. I think that's since been fixed, and this could be a fixed issue, but I'm not particularly sure. So that would affect the precision control, and also there's a rounding control mode for FPU operations in X86, and that is also not yet implemented, but we support the flag, we support setting and reading it, so it'll be also a matter of just putting that code in. SSC support is architecturally implemented. By that, we mean that we have support for the XMM registers. We need a lot more instructions for SSC. Some of these are kind of complicated, and we only really implemented the ones we ran into when translating some of our test applications. But it is possible to implement the rest. It's just a matter of time, and hopefully once this is open source, somebody can take up this task of actually trudging through and implementing those.
So the other benefit that we saw when we created this, and the pattern, the architecture that we conceived of, was that everything is modular. So we go through this pipeline where we start with some kind of native mode application. At the end, we wind up with a blob of LLVM intermediate representation. So when you start from a binary application, and you can use any analysis methodology that you have to produce control flow and data information for that application. So we provide two existing tools. We have an IDA Python script, and we have a native mode program that uses a instruction decoder to perform recursive descent over a binary program. You could also perform this active control flow recovery using a tracing debugger and record the instructions that are executed. And all of that someone needs to do near the left-hand side of this pipeline is take their program and produce a Google Protocol buffer data blob that conforms to the specification that we provide. So once they have the control flow and module information in that protocol buffer, our translation library / tool will read that information and produce well-formed LLVM out the other end. And then that well-formed LLVM can then be used at any point inside of the LLVM analysis or compilation or transformation process, independently of its original source. So all of these individual components can sort of be like mixed and matched. So if you wanted to take our instruction translator and use it independent of this entire system construction effort, if you had a small stream of instructions that you simply wanted semantics for, you could use it for that purpose too. So we think that that makes it much more useful.
So we talked a bunch about control flow recovery. When we originally started this, it was like, oh, control flow recovery on like normal compiled binaries. So we're just going to start at the entry point. We're going to do a breadth first search through all your discovered basic blocks. You're going to do some hand waving, and then you're going to have your CFG. Like, what's the problem? This is pretty easy. And then we actually started doing it, and then you run into all these problems. So first thing you run into is you have indirect calls where you're jumping via register, and you're like, oh, well, what do I do here? This is a little confusing, but you can deal with that. And then you run into jump tables, and if you want to accurately translate this, you need to find the jump table and see all of the possible options that you could jump to accurately model this in LLVM. And after you deal with that, you're into things where the compiler sees oh, I have this constant string, and I have this padding between these two functions, and I'm just going to put it there. And then some of these strings can disassemble for a really long time. And you think, oh, this is, moving a reference from the code section. This is obviously going to be some code that's going to be a function pointer. I should disassemble this and treat it as a function. And then you find out you're really wrong. And then you have these really confusing things where you have an immediate value, and you have to think to yourself okay, this could be a constant, or this could be referencing code somewhere nearby as a function pointer, or maybe it's really referencing something that's code as a data section, and I'm not really sure what it is. And the answer is really pretty critical if I want everything to work right. So what do you do about this? One of the big helps when our recursive descent disassembler was that relocation entries are awesome. They're required for ASLR to work, because in ASLR you're going to R the ASL, and and so once you move things around in memory, you need to know how you should modify all the pointers there. So your location entries are going to reliably help you identify all the pointers. That was really helpful. The other thing is you have API domain knowledge. So if you have a call to create thread, you know for sure that one of those arguments is going to be a function pointer, and you need to create a new entry point in your binary for that. And if you want to re-emit this code and have it work later, you're going to need to know about the APIs anyway, so you might as well use that knowledge since you already have it. But after spending a lot of time writing this recursive descent disassembler, we found out that it's really best to just let IDA do this. They've invested I don't know how many countless man hours into getting control flow working right for all kinds of architectures, and especially various Windows binaries, and it's pretty awesome. It just works. It's really great. And so we wrote up an IDA Python script to just take your control flow in IDA and re-emit it as a Google protobuf thing. And writing this script essentially took about a week and a half, most of which was me learning IDA Python. So that just showed that it was the flexibility of our control flow recovery and translation separation. Had we tightly coupled those, this would have turned into another nightmare. The great thing is you can also, you don't have to accept just the default control flow that IDA recovers. Your control flow recovery is going to be at least as good as what you see in IDA by default. You can look through the IDB yourself, and you can mark things up as code, data, add new functions, and then you can run our IDA Python script on that. So you could potentially have a manually verified, really good control flow solution. And IDA provides this cool control flow editor that you can use yourself because it's IDA.
So we have some ideas on how to perform control flow recovery inside of our framework in the future. There has been some work done by this group in France called the Insight group. They weren't on the prior work slide because they don't translate to LLVM, although I'm trying to persuade them that it's a good idea. They have a very elegant and excellent framework that translates their native code into their intermediate representation, and then they perform symbolic execution on their intermediate representation to derive more control flow targets. And their system works, and you can clone it from Git today and fire it up on some native programs, and it will tell you what the control flow targets are, and I'll give you, if we have time, a short demo at the end. But we could do that too. We could have symbolic execution on our generated LLVM IR in sort of a partial form, get as far as we can using either a linear or a recursive descent strategy until we reach something that we can't see through, perform symbolic execution until we can see through it, and then switch back and forth between these two modes until we run out of code to disassemble. So that would be a big help and assistance, and I think would be pretty cool. So what I would like to talk about now is sort of some nitty-gritty details of how our translator works. So LLVM requires there to be at least one function inside of a module. So a module is seen as a compilation unit inside of the LLVM framework. You compile one C file, you get one module file. You can link module files together to produce an ultimate executable. But in the beginning, there's one compilation unit, one module. So we make one function, or at least one function. This function accepts a single parameter, and that parameter is a register context structure. That register context structure, really more a machine context structure, defines every element, every mutable element that code could modify. So it contains integers, it contains flags, it contains XMM registers, it contains everything to do with FPU. Conceptually, it would also contain system memory. So every time we translate an instruction, say we translate a push instruction, we model the push instruction as we read from a particular element inside of this translation context, and then we write that element to a memory location, and then we update the stack pointer inside of the translation context. And then this is how all of our rules for translating individual instructions tie back to what we see as the original machine state. So this is also how we deal with calling conventions. We don't really care about calling conventions if we call some subprocedure, because every time we call a subprocedure or we return from our current procedure, we take everything that is in the current context and we either pass it to our callee or we hand it back to our caller. So this means that any modification that a procedure makes to its local registers or local state is visible at the appropriate time to the caller and the callees. So we have a short demo there is one. So we have a change to how we modify e-flags. So it used to be that a lot of projects would attempt to model e-flags very faithfully. They would say that e-flags was a 32-bit D word, and then anything that modified ZF or PF would compute the bit that should be at the appropriate position inside of e-flags and then blast the bit into that location inside of e-flags by ANDing and assigning. And this is very annoying to analyze statically. So we modified, we didn't modify, we created our framework such that all of the flags are 1-bit values, actually. And every time an instruction produces a flag, that value is in the translation context is set. So this means that the stock compiler optimizations and transformations are able to take comparison operations that set, say, ZF, and then branching instructions that read ZF, and it's able to completely remove ZF from the final code and it ties the branching operation back to where the comparison operation is performed. And this helps in two ways that are sort of related. One, it makes the code more succinct, and so there's less of it, and it's also faster. And it also, I think, makes the code easier to understand, because where previously you were trying to tie these two actions together inside of your head, that's now made explicit for you. So one thing that I was interested in when we started this project was, can optimization make code understanding easier? And I think the answer is yes. So now we have a demo where we can sort of do a low-level walkthrough of...
So we did a lot of talking about like register contexts and flags registers. So now we're actually going to try to show you how this looks like in LLVM by showing you one of our simple test examples. Like we actually have like a bunch of tests with McSema, and we run these tests like once we make modifications to make sure it still works. Like I know it's a pretty novel concept. Yes, test.
I read about these in school.
Oh yeah, fonts. That's not going to do. There we go.
We got both kinds.
Yeah. So this is one of our test batch files, slightly modified to emit, to disassemble the bitcode into the, like disassemble binary bitcode into textual bitcode, so I can show it to you. What we're going to do is we're going to take an assembly file called demo test2.asm. We're going to build an object file out of it, and then we're going to translate it with McSema, optimize the translation, and then we're going to essentially rebuild a driver for it and show you how to link with McSema generated code. So let's start by looking at the assembly file. This is a very simple assembly procedure. It takes one argument in EAX, and it doubles the number 1 EAX times. And the reason we chose this is it includes some bit operations, includes some arithmetic operations, and it has a loop. And it was meant to be as a very simple test. So now we're going to run this batch file, and then I'll show you some of the intermediate steps. OK, let's see here. So let's first look at the unoptimized LLVM. So remember we said there was a register context? So that code got translated into one function. It's called function, well, sub1 here. The sub takes one register context, which is the pointer to a struct regs. You can see the declaration for struct regs here, which is basically holds all of the registers, kind of obvious. And upon every function entry, what we do is we spill the context from the structure to a set of local variables. The reason we do this is it helps to, when in the optimization phase, it's much easier for the optimizer to deal with local variables than it is for it to deal with globals. And so this is us spilling stuff. And we can fast forward ahead. And you saw there was a bunch of increment operations and some loops. And like, hey, like we're adding 1 to stuff. There's a loop here. You can see that we have some of the registers names, like we're reading stuff for ECX. Loop exit. And then at the very end, we do the opposite of spilling, and we store the locals back into the global context for return from this function and possibly back to another McSema procedure. Now let's look at the optimized code. Looks very similar, but you'll notice that there's still some. So the optimizer number 1 isn't perfect. For instance,
Caps?
yeah. For instance, like it spills and stores the SSE registers. Like we don't use SSE in this procedure, so there's still some work to be done. But for example, a lot of the code is there's much, much less code. I know it's hard to see from the text file, but if you just look at the amount of text, there's about 1/3 less code in the optimized version that the optimizer was able to get rid of us and to make our lazy translation better.
when you work with this, you can kind of glaze over all of the state
Yeah.
stuff.
I just wanted to show you how it looks like in the actual LLVM bit code. And now let's take a look at how we would talk to this translated assembly code. So like we define the register state as a C header, and you can include the register state, and like you give it a stack, and you give it a value for EAX, and then you call like our translated function, and it'll operate on that register state. And since we return an EAX, you can return this. This is specifically meant to operate on things with unusual calling conventions. If you have a normal function with a traditional calling conventions, like you can get it to automatically generate this for you with like the right amount of arguments, as you saw in the kernel32.dll example. And yeah, like we run it, and let's build our stuff. There, like it ran. Woo! Yeah. And
Oh, thank you.
and there's like a whole bunch of tests. Like we have demos of FPU, we have demos of lifting DLLs. Like some of these actually support multi-threading. Like we can lift like create thread and threaded code, and that also works. And so like we have tests, and like they work.
It's software.
All right, let's continue with our slideshow.
That thing. So I sort of alluded to this earlier. We model all of our changes to mutable state in registers into this register context structure. But currently, we model memory simply as memory. So LLVM load and store instructions result in loads and stores into the sort of current process context. So if a piece of translated code reads or writes to memory, it doesn't read or write to a sort of shadow state. It reads or writes to its the containing process's memory. You can override this with a translation pass that replaces all of the loads and stores inside of our generated code with functions that you can provide. In the future, it's conceivable that we would proxy memory through some kind of representation inside of the register context structure, but we haven't done that yet. Another limitation of the translation approach that we took is that since we model every read and write through memory as just loads and stores through memory, this is also how we model stack accesses, so pushes and pops, and reads and writes to the stack are modeled this way. This results in some code blow up when you take a C procedure that uses local variables that are stack allocated and compile it and then translate it back, because every access of those stack allocated variable will be a read or a write through memory. What would be ideal is if our framework could detect where the local variables were inside of a procedure and replace them inside of our generated LLVM with allocated LLVM variables. And then LLVM can replace them with values by promoting everything to a pruned SSA form. However, variable recovery is kind of non-ideal. There aren't very many good algorithms to do this. And the algorithms that exist have hideously long running times and imprecision and unsoundness. So that's kind of frustrating, and it has sort of dimmed my desire to go and implement these frameworks and algorithms inside of our tool. But other people could do it, and perhaps I will feel better about it later and do it in the future. So we talked about how this, we showed a little demo of how this worked, but this is sort of a conceptual diagram. Say on the left, we have some native procedure that takes two parameters, A and B, that are on the stack. So we read them into EAX and EBX and sum them and then return. When we have the code translated, everything is kind of noisy. We read all of the values out, and then we operate on them, and then we push all of the values back into our calling provided context. However, something that's kind of neat is that the optimizer can look at this sort of messy generated code that we've produced and say, oh, well, this isn't needed and that isn't needed. This happens a lot for flags, because if flag operations result in bits being set that are never used and are then destroyed by following like logical or arithmetic operations, the optimizer can say, well, this particular flag set is dead, so I'm going to remove it. And then everything that produces this flag set is also dead, so I'm going to remove that too. So this means that you wind up with instructions, and the LLVM code that you have at the end is only the LLVM code that the optimizer has determined is necessary to produce a value according to the semantics of LLVM, which we have honored while performing our translation. So everything should be okay. And it has been. And during this project, I actually spent more time than I would care to admit chasing some bugs that were not actual bugs, because I would write a procedure in hand-coded assembler, and I would translate it, and I would expect there to be a loop. I would say, oh yes, this will be a loop, and it will count like so. And the generated code that LLVM's optimizer would kick back to me would just be return 0. And I would say, oh, that's not right. And then I would think, oh boy, there's some subtle bug somewhere inside of how I compute some flag that's used, or something, or perhaps there's even an LLVM optimizer bug. Because when you are doing compiler development, you actually have a small license to claim credit for compiler bugs. And then I would look at my code, and I would realize that what I was doing is I was looping, say, ECX times, but I was always adding 0 to 0. And the optimizer looked at this and understood it, and it said, you're not doing anything. And then it removed the thing the loop was doing. And then it looks at the loop, and it says, oh, the loop isn't doing anything either, and it removes that. So frequently, this framework will tell me things about code that I wrote that I didn't know, which is kind of fun.
So eventually, whenever you're translating real executables, especially in Windows, you're going to run into external API calls. So how do we deal with these external APIs? Well, we thought about it, and we decided to create this web-scale database, otherwise known as a text file, to take all of the Windows API signatures that we could gather and put them into one simple, easy-to-use format. Essentially, this is a giant file that is included in our open source distribution. It includes DLL name, export, how many D words it pushes onto the stack, and the calling convention. Also supports doing calls by ordinal, by the way. It's an easy text-based format that you can modify. It includes all of the Windows stuff by default, but if you're doing lots of work in some custom application, it's pretty easy to add to by hand or semi-automatically with a simple program. And whenever we're doing translation, if we see an external call and we match the DLL name and the export name, we look in our file, we see if we have a match for it. If so, we emit we see how many arguments it's supposed to put on the stack. We read that many arguments from our register context stack, and then we just emit an LLVM extern that takes that many amount of parameters with the right calling convention. And then when you re-emit the code, we rely on the standard LLVM tools to do the correct invocation and name mangling for us. And so far, that's worked really well. Other than externals, one of the next things you're going to run into when translating real code is these really nasty call register or call memory routines. So what happens when you see a call by register or a call by memory? What you have to do is you have to realize that right now we're in a translation context and we are calling an unknown value. And we don't know whether what we're going to call is other translated code or external or untranslated code. And the reason this is a problem is because McSema takes all code and translate it as a function taking a single argument, which is the register context. And if you pass the register context to code that's not expecting it, it's just going to blow up. And so for the cases where we can't tell, what we have to do is we have to take this register context and we have to make it the same as the native CPU context. This works really well when you're doing a translation from the same architecture to the same architecture. If you were doing this cross-architecture, you could still potentially somehow adapt this. We have all of this code isolated in its own faraway file in a deep, dark corner, which we hope you never have to look at. It's kind of terrible, but it works. And so we take the existing processor context from the translator, we make it the real native CPU context, and we just blindly call that value we were going to call, and we hope it returns. And then when it does, we take the native CPU context at return time, we make it a McSema context, and then we continue on. And this is actually much, much harder to do than it sounds, because you have to worry about when you're making something into native context, you have a translator state that's using all of your native CPU's registers, and you can't really mess those up because you're going to have to continue afterwards. And when you also have to switch stacks from the translator stack to the normal stack, and then switch them back, and then adjust for how much it would have popped things off. And There's like a lot of horrible code here that manipulates some internal Windows data structures and such for the stack switching, and hope you never have to look at it. The other issue that you run into is essentially the inverse, and that's callbacks. So I gave create thread as an example. And create thread's not going to make a McSema CPU context and pass it to your translated function. Like what you have to do is essentially the inverse. You're going to have to write a bunch of code, which we wrote, that doesn't assume a calling convention for your called function and tries to take the native context at that time and with as little tampering as possible, create a McSema context out of it, call the translated McSema function, and then try to restore that restore all the registers from the McSema context back to native context so your callback can continue execution. And like both of these things like actually do work. We have examples for them. So now I want to talk about the stuff we have that is currently supported. So I guess this is like the good news slide. What works? Like integer instructions. Like we have support for a very large amount of the integer arithmetic instructions. Certainly not all of them. We are missing some, but we have unit tests. We have some unit tests that fail because we haven't written the instructions for them yet. So we support a lot of them. We're planning to support more. It's just a matter of writing it. We support the FPU registers and the FPU flags, and we have a fairly large set of the FPU instructions also. But once again, this is incomplete. We support SSC instructions. Our SSC support is currently pretty limited, but hopefully somebody can take up the challenge. And as I mentioned before, like callbacks work, external calls work. We have special handling for jump tables that can recognize them and re-emit them as an LLVM switch statement. So the LLVM optimizer can use that information and make your code better. And we have support for data references. Like if you detect that you're referencing data, we'll try to figure out its size and shove it into its own data section. Now, to see some more of what works and what's possible, we have Andrew to do a quick demo of the possible future.
We have a final demo. I mean, not the final demo, but our final demo. So I'm going to show you some, what? PowerPoint? No. No!
Just press, and show.
I tried to press exit. It didn't let me. So.
You have to move the other screen.
Right. So there's a project on the internet, and they perform integer range analysis of LLVM bitcode. LLVM bitcode is kind of, it's very close to what you would think of in a native context because the integer bit widths, all integers in LLVM are typed by their bit width, and they're neither signed nor unsigned, and the signedness of an LLVM integer value depends entirely on the context which it is used in, which is very similar to how every ISA I can think of uses its integer registers. So these people made this analysis, and they do not know that I'm doing this. I actually have no connection to them. I've never spoken to them. They made an analysis that works on LLVM bitcode. So I took our output from MCSema and fed it to their tool. And what it gives me is it gives me this integer range information for values that are used inside of the program. So if block 11 is the exit block, and you can look down and see that, so some things it derives infinity for. So for example, it says the value of EBX is somewhere between negative and positive infinity, which is an over-approximation, but I mean, it's probably right. However, if you look at the value of EAX, which is sort of in the middle of the screen here, it says that the lowest unsigned and signed value is going to be 0, but the largest unsigned and signed value is going to be -2. Which is kind of interesting. So you can look at this assembly procedure and say this is the range of the output of this particular assembly procedure. And this is an analysis that you can get by taking people's tools that they designed to work on C programs and adapting them to work on binary programs. So that could be neat. One thing we'd like to explore in the future is being able to take information like this. So we can take this information that we get as text output and project it back into our LLVM. We can also take that information and project it back into, say, IDA or some other tool that you're using to understand what a binary program is doing. And then that could tell you more things about what your program is doing. The other short demo I'd like to give is also someone else's tool who also doesn't know that I'm doing this. This is an output from a symbolic execution-based control flow recovery framework from Insight. There are these two procedures, foo and bar. One performs addition, one performs multiplication. They are both invoked via function pointer from this particular program that I've compiled. So there's a call EAX down here. And the symbolic execution system has discovered that EAX can be a jump to either foo or bar. And I believe deep down it sort of knows what the conditions are for that jump too. It just chooses not to tell us. So, and then it adds them both to the program disassembly here. So this is the kind of information that you can incorporate, and we can incorporate into our framework once we have our code inside of a intermediate representation.
I guess this is like the sad slide of what doesn't work yet. As I said, we need support for more FPU and SSE instructions. Exceptions, exceptions is a real challenge because let's say you're going to divide by 0. Your division by 0 is going to happen in the middle of translated code, but the exception information you're going to get has stuff for the native CPU. And how do you interpret that in your translated code? You're not even sure what architecture you're going to be running on. So this is a kind of a big problem which we don't have a solid solution for yet, but we are thinking about it.
No one else does either.
Yeah, so I don't feel bad.
No.
Privileged instructions. We did this to model user code, so we haven't touched any of the privileged instructions for X86. And of course, we need more unit tests. And as you saw from, I don't know if any of you caught the size of the kernel 32 DLL that we emitted, but it was 6 megs. And it didn't take all of the input functions. So we still need some better optimization. And we think that this is possible. We have some ideas on how to do this. And especially if we can do better control flow recovery and eliminate these context spills and stores, those take up a lot of code. So ideally we'd be able to get rid of those and we could really start trimming things down. Now Andrew's going to talk a little more about some other future plans.
Yeah, things in the future. So we can support more instructions. At this point, it's just a matter of sitting down with your favorite copy of the Intel manual and asking, what does add really do? We've done add. Don't worry, it's there. What does punpack LQDQ really do? And writing it down in using our framework in LLVM. We can perform additional optimization. We can perform memory modeling. We could change our view of the stack so that it's an array instead of an anonymous slab of memory, which is a slight simplification and is not entirely true all of the time for all programs, but could help with variable recovery. And we can continue to perform our traditional level of rigorous testing. And then we can also release the code. So that's us. Any questions?
Was the information contained in TableGen and LLVM of any use into generating those micro operations back into IR?
Not really. So when I looked at the information inside of TableGen, it didn't have stuff like flag set. There are some, like Dagger and Fracture both tried to go backwards from TableGen into LLVM. So we do use it because we use LLVM's instruction decoder. So we use LLVM's instruction decoder to produce mnemonics and opcode decodings for all of the instructions that we translate, but we don't rely on TableGen for semantics.
Great, thank you.
Do you have any plans for self-modifying code or other stuff that doesn't fit into ADA's model, such as jumping into offsets of already existing instructions?
So the second half we kind of already deal with inside of our bin descend program because we don't have a very tight correlation between an instruction and its location inside of the binary. As soon as we identify that some offset inside of the binary can be used as an instruction, we just yank it out. So there are some things that IDA does that we don't, like identifying that there's an implicit branch between one block and another block that results from a third block branching into the middle of a larger block. So we don't do that. We just copy blocks, and it results in a much larger control flow graph. But it does mean that we can deal with sub-instruction branching. Your first question, right, self-modifying code. So The only, like, I'm aware of, I think a research paper that deals with self-modifying code via like a contextually aware control flow graph. So this is another reason why we abstracted control flow recovery from LLVM, is that once you, like, if you're capable of sort of unraveling the self-modifying code to a point where you have descriptions of like all of the different instructions that could execute and in what order, you can take that described as a control flow graph inside of protocol buffer and translate it into LLVM, and then things should work. But that's me telling you, go solve this problem first and then come back to me and I can help you, which is something I love doing but doesn't really help you too much.
Have you tried to run a program through LLVM obfuscator, obfuscate the code, and then retranslate it through your tool to see if the optimization steps will deobfuscate the code?
We have done this for some, I mean, we've done something similar for different, like, not exactly that experiment, no. So I wrote a previous instruction semantics project once that would do this for string obfuscators, where like the obfuscation would work off of 2's complement subtraction from 0 to build up a string on the stack, and very basic like constant folding optimizations removed the obfuscation to build obfuscated strings. So this has the same or better optimizations than that does. So I'm pretty confident that for some types of obfuscations that would work. Some things that are difficult to see through are things like reading and like reads and writes to memory. The optimizers kind of need to either infer or be told like smart things about that the contents of memory won't change out from underneath them. So
Yeah, and like sometimes the optimizer works scarily well. Like I remember a few times we were doing examples, and like the LLVM code would be like the final emitted object would be smaller than the input object. Yes. And we're like, what's going on? Like, did we break something? And like, the optimizer just detect an optimization that the original compiler didn't.
I just have a question about C++ code. If you have code that's been generated C++, where you have these V tables, cores everywhere, how do you cope with that? Do you have any sort of tricks, particular optimizations for this type of code?
So we can deal with, like, so since we're calling convention agnostic and we also deal with calls through registers, we can deal with calls to like member functions that are invoked through vtables just fine. The trick that we have, like the problem we have with C++ right now is in recode generation, because if we take a, like if say if we see new, and new will be a mangled name inside of, by different C++ standard libraries. So if we encounter it during like control flow recovery and when we're promoting it back up into LLVM, we look at it and we ask, well, what is this symbol? Like, what does it mean? It's mangled. If we attempt to treat it as just some kind of like standard call or cdecal function, when we have LLVM regenerated, LLVM will remangle this already mangled name using that calling convention, and then nothing will work. So, or we could say, well, let's try and unmangle this name, but which unmangling scheme do we use? Which, like, and I'm not entirely sure at this point what to do about that. Like, do we try them all? And like, if one produces something that is like sufficiently ASCII-ish, do we roll with that? Do we have some kind of measure of what is sufficiently demangled for us to use as a name? So conceptual support is there because of the calling convention agnosticism of the way that we do subprocedure invocations, but some of the machinery isn't there to support the full end-to-end system yet.
Yeah, so we could probably take it to LLVM, but not emit it back out.
Yeah. Right. Oh, yeah.
All right, thanks.